Okay, so let's try to see how we can think these all the discussion we have done so far. So here, this what the textbook did is they use lysine as an example. They can show you that it has multiple equilibrium. For example, I'll write one later on. So when it's fully protonated, it has 2 positive charge because we'll come back to show you what that is. And then the first dissociation and second dissociation and so on and so forth. So they create a different species. And you notice different species each species has a different charge. Some of the 2+, some of the 1-, and 1+, some of them neutral. So similarly on the protein, depending on what pH you have, you can think of protein is even more complex, multi-proton donating accepting molecule. So but we can use amino acids to demonstrate how can we think about the isoelectric point quantitatively using the acid-phase equilibrium. Now, but here is the background. You know experimentally you can find the isoelectric point by what Nick was describing when we learned in the Chem432. So when the protein at any random pH, they have a charge, they will move in the electrical field. So if you have a gradient in what we call isoelectric focusing gel apparatus, the molecule is going to keep moving until they hit the zone where the pH in that zone made the protein neutral. They will stay there. So the protein bands get very, very sharp. So that's the one we can see. So what you were actually doing is you can also use these equations, which is kind of very complicated, but I want to find a simplified way to think about it. And so you can do this, but this generic approach has one advantage. They can tell you how each of the different species fraction changing as the pH moving. But so this is a very generic approach to this. But let's try to look at this in much more in a simplified way. Let's focus on what the PI is. So I can write amino acids in a sort of a generic form first. So let's just say we present amino acids using like what we typically put an R group here, put an H here, then now we just put NH2 here, right? So but since it's a weak acid, which means in the solution when you put it in, this guy is going to pick up a proton. So we can actually just write. So now if this guy can have 2 categories, right? So we can, like I said, with lysine case or arginine case, then this R could pick up another proton, or we can just simply write something like this. Or if they're in the cases where it's glue or acid, and then there can be another donor group, or this could be a carboxylate case. So that's how we can just generic. So let's use. So we have neutral amino acids, and then this is basic, this acidic. Now each of this, they have different tendency to have a PI. So the PI now we're talking about is we basically make amino acids to be representative of protein. Now we want to think about how to calculate the PI of a amino acids, which is kind of an example, we call it model or simplified case. So instead of me writing this over and over again, I'm just going to use neutral amino acids as an example. So I can say this is the amino acid. A stands for what it is. And then I can say for neutral amino acids, because the side chain, we have an amino group. So I just say I have one amino group to the left. And then of course there's another proton that's ready to dissociate it. I can use the right one to express what it's going to dissociate, right? So this is just easy for me to write. I don't have to draw this every time. So basically, if you do this, then obviously at this stage, for a neutral amino acid, at the very beginning, they have 1 positive charge on it, right? Because if I just have, let's say, a alanine, this is a methyl group, then this is carboxylate has loaded a hydrogen already. This one picked up a proton because it's weak base. So this basically is the basic form of amino acids when it exists in the solution at neutral pH. This is how you can think of it, the starting point. Now, so if we look at a neutral amino acid to begin with, and then you would have a situation, well, first, this guy is plus water, it'll dissociate as HA, then, so let's call this is the first dissociation constant. Then the second proton would also give out after the very first one gave out, so the carboxyl. You can write this as, in essence, this would have A negative and A positive because we call it Zwitter ion. But in total, the Zwitter ion is neutral, so we can kind of think of it as neutral. But internally, there's actually a carboxylate group, and there's a protonated amino group. But they can be represented like this because they don't have charge on them. Now, this one can further dissociate. So we ask ourselves, if I tell you, I know the pKa of this two reaction, what is the pI for this amino acids and all the species to be neutral in solution? So that's basically the question in here we're trying to answer. So obviously, you can go back to use that book. The textbook's approach, you're going to go very complicated process. Figure out at every fraction point, which whatever that is, then you will find a pH. But there is actually an easy way to do it. Aaron? Test yourself to see whether your intuition really teach you something about your own thinking process. So Aaron says the pI equals half of pKa1, pKa2. Is this really true? So, well, we have this intuition. I think it's somewhere in between, right? No, so what we do is let's just, if we don't know anything, we want to know something about, obviously this type of question always relate basically is the pH point, right? So pI is a pH at which they charge you. So we're described a situation where we want to know the relationship between the pH and the positive and negative charges. Then we want them to be the same, right? That's virtually what we're dealing with. So if we don't know what to do, just write out the equation in this case. So this equation basically relates the pK of each of the constant, the pH. Equation also gives us a chance to examine the concentration of positive charge or negative charge species. And because we know what we want to do, we want to find a pH where positive and negative charge species should be equal. That's our goal, right? So if we don't know what to do, we just write it out to see what they look like and whether can we analyze this. So if we actually use that simple-minded approach, we just go, okay, well, let me write out Ka1 basically is the equilibrium. Now, we're assuming it's very diluted, so we use the concentration direct as an effective concentration. So it'll be something like the concentration of this, the concentration of proton divided by. So that's basically the first one. So obviously this water is a pure liquid, so we don't really put it into the equation. Now Ka2 equally, we can write out. So we would have A minus, and then divided by. So let's take out some observation to think about it. So obviously in either PI, so let's think about what we want to do here. So at PI, which is also the pH, where if you imagine if these molecules spread out on the protein, I want the contribution of this to the overall protein should be negative, although should be neutral, no more charge. That means, so if it's an isoelectric point, so that means all the negative species and the positive, their concentration should be equal. Isn't that right? So that's a good sense. So the neutral one, I don't care. But so in this case, who is the negative? Well, the positive guy is this guy, right? And in here, the negative guy is this guy. So this actually gives us a good entry point. We said, well, wait a minute. So that means whatever the pH I put in, I'm arrive at an equilibrium where this guy's concentration and this guy's concentration are equal. So then what do I do if that is the case? I think I give some enough hint. I hope people can do the next step to check if Aaron's intuition is actually true or false. So now I just said, we wrote out the equation. This equation gave us an ability to observe how each species in this equilibrium is going to be affected by proton concentration and the Ka. So that's the definition of equilibrium constant, right? So we just did that, and then we keep focusing on the question we want to go after, which is we want to find a pH or proton concentration at which the negative species and positive species are equal. So therefore, there's no net contribution of charge by these amino acids to the situation or to the protein. Now, so that means this constant we know at a certain this proton concentration has to make in this double equilibrium these species and this species have the same concentration. So now when that is known, what do I do next?
Would you like rearrange it and substitute in?
So you can either rearrange, or you can, if you have two equations that's equal to each other, well, are both true. When you time the two equations, what happens? The equation still be true, right? Mm-hmm. So and we did so if this equation is true, this equation is true. If they time to, if this guy times to this guy, what happens? So I'm just taking the next one. Maybe, I don't know if this is exactly what you're saying, but this is almost, think of them being a rearrangement, but not simple rearrangement. But
Can you cancel?
okay, basically, Kaya said that this is neutral, even though the neutral there get canceled. And we said we want to find the pH at that point. This guy should be equal, because that's our condition. We obviously the pH can be anything, so this guy can. If the pH is really, really low, I have a lot of this. If the pH is really, really high, I have a lot of this. It's equivalent to one of these things going on. But I really don't care about all these other things. I just want to find a point where the pH happen to be when these two guys are equal. Oh, then that's simple. So now all of a sudden we have Ka1 times Ka2 squared. So then the proton concentration really is the square root of Ka1, Ka2, obviously pH half of Ka1. Does this make sense? Any question?
Do we have to know the math to get to the pH part? That's a lot of math.
Which, oh, you mean this part?
Yeah.
Oh, okay. So, okay, pH is, now we assume the concentration is, so negative log square root basically is so then this is pH, this is basically pKa, 1/2 of log Ka. Does this help?
Yes.
All right, so I don't think I have any time to finish this, but this is actually a good way to stop here. But I do want to give you a hint on how to do the homework. This actually is a homework, one of the questions. So, so how do we do? So you might say, gee, you pick an easy one to do the demo. So why don't you do the harder one? Now, let me actually just quickly end here by just give you a hint, because you're supposed to still do the homework. So I don't want to finish the rest of it. So let's just say I'm dealing with lysine now. So I don't have this situation. So I have lysine, then the left side, the side chain got another proton on it. So basically you would have a amino acids, let's call this lysine, and then we have this, and then we have these and the 2 plus, right? Because then we got 1 plus, you got another plus. So virtually you would have a H2A 2 plus. One plus. Now then you have a, that's your Ka1. Then this, now all of a sudden the remaining dissociation will be the same. So this guy will continue with Ka2, and this one will become Ka3. Now, yeah, so what the homework want to do is, they want you find the pi of this to be half of this. Now my hint, it's the same principle here. The only hint that I can give you is that when the pH is in between here, most of this species become negligible, because they'll all be fully dissociated. There's not much of this 2 plus left. So again, goes back to this plot. If you are in this region, this guy becomes 0. So you can use the reasonable assumption by saying, I can ignore this whole thing. So there's the contribution of this guy in the charge process all gone. So all you need to just focus on find a situation where this guy and this guy to be equal. So similarly, when you do the other situation, the aspartic acid, then you would have something different. So it's the Ka1, Ka2 is where you need the species to be equal. So I'm not finishing it because you will get a chance to work on this on your own by doing the homework. But if we have questions, of course, we can come back, look at the homework answer key, and also you can look at how we derived this one, and you should be pretty clear, especially when I tell you for basic or acidic amino acids, although there are 3 Ka, you only use 2 that to look at the isoelectric point. The 2 you use is where they're actually the neutral species being sandwiched by either positive or negative charge. That's the rule of thumb here. So obviously, in the lysine case, it is this second step. So the pKa certainly is on the Ka2, Ka3. Where aspartic acids or glutamic acids, it was the first step, 2 step. And come on, think about what that is. And then there is going to be a chance for you to practice on this at homework. Okay, so I know you have a homework due today, and you have a homework for the spring break sample exam.